Welcome back to another episode of Adventures in Machine Learning. I'm one of your hosts, Michael Burke, and I do data engineering and machine learning at Databricks. And I'm joined by my wonderful co-host,
Ben Wilson. I work on tutorials at Databricks.
Thank you for your service, part 15. So Davis King is our guest today. He is a software engineer through and through and an avid gamer, as we just learned before kicking off the recording, and a real pro. He has an undergraduate and master's degree in computer science and has worked as a software engineer at MIT Lincoln Labs, at Shell, and is currently a perception engineer at Aurora, which focuses on sort of modifying cars to make them self-driving instead of actually producing a new car that is self-driving out of the factory. When not working full-time jobs, he's building and maintaining Dlib, a C++ library of machine learning and computer vision tools. So, Davis, why did you decide to build Dlib? What's the inception story?
Yeah, there's not really a story. I mean, when I get bored, I work. That's like a big part of the truth of it. So I'm like, gotta do something. I have like a wood shop in my basement now that I own a house now. I'm old enough to have a house, and so like I go make furniture sometimes. Not that often, but like, yeah. So Dlib though, right? It started in college, I guess freshman year of college in like 2000. So it's like, oh my God, it's like 22 years ago. Maybe it was at the end of the freshman year. I had taken this class. I mean, I love writing software. I've written software since I was a little kid. But like the software before that is not like on the internet anywhere. It's just I still have it on my share drive down in my basement. But like no one wants to see it. It's horrible. I mean, it's not horrible, but it's not Dlib. So I took this.
What were your first projects out of curiosity, and like what age did you start?
I started at like, we had a Macintosh when I was real little, and you can't program on that. I mean, yeah, you can. There's software on it, but like that's not. I don't know if we did that. We got a PC. I want to say junior high, so maybe I was like 12. It was around the time like the internet became a thing, like when Prodigy and Comcast were a thing. So yeah, maybe I was 12. I think it was like junior high. It was before high school, but not grade school. And like some of my friends were into it. I was like, it's like what your friends are into, right? And so like some of my friends were into computers a little bit, and we were like, we should all learn to program assembly because assembly is like that's like the beginning. You should start at the beginning. Like, we don't know. So we read The Art of Assembly, which is this book that I don't know if anybody knows about anymore, but like it's a book that tells you like how computer architectures work and assembly. It sounds way cooler than it was. When we wrote some assembly programs and goof around and like never made anything big. It's not like we write. You read stories about like the guy who made like Roller Coaster Tycoon like wrote it all as assembly. I think, right? Is that the game? That's that.
The first one.
I think so.
Yeah.
Right? And it's like totally written. So we didn't do that. We wrote like dumb little things that like break each other's computers basically. This is back on like DOS when you could like you could do anything and just wreck your computer. So but it was, I don't know, it was cool. We learned to program, and then I try to remember the progression of it. And then like one of my friends, the guy I was telling you about before, I worked at a hedge fund for a little while. And like one of the guys there was the best man at my wedding. And like we were friends back when we were kids. I remember having a conversation with him. He was like, we should learn Visual Basic because you can make visual programs and it's really cool. And I was like, nah, it's got basic in the name. That's lame. And I like learned C++. And he learned C++ too. And then I don't know, just kind of went from there. We wrote little like silly games and nothing too exciting. But then we went to college and like became real engineers and wrote all kinds of stuff.
Nice. And so Dlib was just, you're bored on a Friday night, let's build something?
Well, sort of. So I took this class. This is class secrets at Ohio State called like, what's it called? Called like Resolve or something. They have this group there called the Reusable Software Group or something like that. I forget the name. And there are like a bunch of people. They're all about like proving programs formally correct. And they're super into like design by contract and like contract programming. And like the end state of that research chain, should it ever really come to pass, would be like a compiler that like proves programs correct. And so like you write a function and you write some contract. So it's like, these are the preconditions of the function. And, as long as the caller upholds those, this is what's going to happen. And you can imagine like chaining together proofs to like prove large programs are correct by looking at like, if I'm going to call this function, right here, I have some big function. I'm going to call this function in the middle of it. Like, can I prove that its preconditions are all satisfied? And then you can chain all it together. I mean, this has not come to pass, right? Like, otherwise we would all know about it and it'd be like standard practice. The wrinkle is like writing the contracts of sufficient clarity such that they can be proved turns into like a problem that is of similar difficulty to programming, to like writing the code in the first place. And then you're like, oh, we're back where we started. But there's like a kernel or there's more than a kernel. There's a lot of like incredible utility there. So anyway, I took this class sequence, and the thing that bothered me is that like, or I should say like, they're right. All that like contract programming and all that stuff is so right. Whenever I tell people this who aren't like familiar with this like area of computer science, they're like, that doesn't sound like that big of a deal. I submit to you, it's the best thing I've ever learned in computer science. Like, of all the machine learning and computer vision and like all the stuff that like people hire me to do, like that's all secondary. No one believes me. You guys don't believe me.
But no, I mean, that's basically, you don't have to unit test if you have a framework like that. And at compile time, you have confidence and safety in what it is that you just created.
Oh, well, yeah, if we had that, but I don't have, that doesn't exist. The part that's the good part, well, that you can like actually have in real life is just contracts, like clarity on what functions do. So like if you want to, you're going to call a function, you should be able to like reason about it before you run it, that like, yeah, this is right, I'm doing it correctly. Whereas that's not common in large parts of our industry, right? There are functions you can call, or like there are whole libraries you can call, or like in Python, where like the culture is sort of like the docs are really unclear, if there's docs at all. And then the way people do it is like they call it and see if it works. They're like, well, I called it once and it worked, therefore I'm probably calling it correct. And you're like, that's not right. Like, that's not really true. So you get these like brittle software out of it. And the whole thing about like that whole field is they sort of beat it into you. They're like, all right, here's how you can here's how you can analyze and reason about large scale software systems. And so this all sounds like a tangent. So I got out of that class. It's like a whole year-long thing. And then it continues on. It's up level because it's like the people who run the whole department there are like super into it at Ohio State, which is really good. So get out of it. And the thing about it is like, you can't really write software. If you want to like do this stuff where you're like, I'm going to be really confident that my program is right and really confident that the thing I wrote makes sense. If you're going to write a function that's going to have contracts on itself, that's like pretty clear, maybe not formally provable because it's hard and the compilers don't exist really. But you're going to want to call libraries, and those libraries, if they have those functions, they have ambiguous contracts or like no contract, like no documentation, then you're not going to be able to make any kind of claim about like your own contract, right? It's like, if these 5 things are true, then this function is going to do this thing. You can't really make that claim because as soon as you call something that has an ambiguous contract, you're like, maybe. So like that was what started Dlib. I was like, I need a library of stuff that has really good contracts that I can just go use on projects. That's totally how it started. Like and if you look at what Dlib is, right? There's like every function has these like really like nitpicky contracts that say like what all the preconditions are and what things do. And that's
but, I mean, on top of that though, there's a sentence in your docs on the main page that resonates with me more clearly and profoundly than any other sentence I've read in source docs. And you probably know which one I'm talking about, but I'll read it for the listeners.
Yeah, I think I know which one it is. Yeah, read it.
I consider the documentation to be the most important part of the library. That sentence.
Right.
And if anybody is curious, please do check out the Dlib C++ library documentation. you will see the most comprehensive API docs with full explanations of what Davis is talking about, those contracts. Like, this is what this thing does. Here's a usable example that proves it does what I'm saying that it does. And here's my allowable inputs, and this is the output that you would get. And it allows interface. I just think about what would the ecosystem look like for Python ML in particular if every library did that.
Yeah, it would be a big deal, right? This is not like I didn't invent this thing. I'm saying, I've totally learned this from people at Ohio State who are part of some wider community that this has been going on forever. But it's so profoundly useful that, yeah, I really wish everything was like that. Because sometimes the problem is as soon as you start interacting with libraries that aren't like that, you then have to lower yourself to their level of contract clarity, and then your software becomes unclear. And then when things break, sorry, I keep clearing my throat. But the things break, it's unclear why, right? You run a piece of software. I'm sure you guys have seen this example I'm about to give a million times. Someone's running some piece of software and something bad happens. It maybe crashes or gives a bad result or whatever. Something, it doesn't work the way it's supposed to, and everyone's unhappy. And then someone says, well, why does that happen? And they start looking at the code. And then maybe it's crashing. So they go into some function and they find the array, say that it's indexing out of bounds, and then it's blowing up. And so then the question is where's the error? Is the error in that function that has the index out of bounds in it? Or was that function itself, did it have a precondition that was violated by the caller? And so the error is actually in the caller. And if that function doesn't have documentation that says what the preconditions are, then you just don't know, right? And then maybe the person doesn't, or a lot of times it's in someone's head somewhere. Really, they have a fuzzy idea about it, but if you talk to them, they'll be the error, we should fix the caller, not the callee. But maybe someone new's coming to the project and they're editing it, and they just put some weird hack in there that says okay, if the number is bigger than the array index, then do some off the wall thing that makes it not crash. But that then complicates the function it's in, and now that becomes part of the supported behavior of that function. Where you're normally it does the normal thing it does, but then if you give it a number that's bigger than 5, it does this other thing, and then someone else notices that, and then they then depend on that behavior, and then eventually the function is just whatever the implied contract is so bizarre no one can understand it, and no one can ever change it. And then someone comes along later and they're why do we do this? We should make this cleaned up. And they try to, they try to change something that ought to work because they have some conception of the contract in their head that's different than this other more complicated weird one. And then they edit it and it all seems fine to them. But then, there's some other client that uses it that runs only on Tuesdays. And they land their code and on a Wednesday, and then a week later everything's on fire all of a sudden, and you're why did that happen, right? And it's all because the contracts were bad. You know what I mean? It's just, yeah, contracts are life, and I try
I think you just absolutely perfectly described the pain that is open source software management, where you have a lot of contributors, and if maintainers, who are the judge and jury of code getting merged in, if they're not scrutinizing changes like that and saying, hey, this function is actually doing too much, or hey, you're bolting on this additional functionality into this method in this class, it should really be a subclass of this instantiation, and not, let's introduce abstraction here. And I've personally seen exactly what you described, where it's somebody's well-intentioned. They come in, they say, well, it is failing for this use case, and the behavior isn't quite what we want. And without looking at what that API contract is coming into using that function, and realizing that we're actually inadvertently, because it's in Python, we can get away with overloading a method without any ill adverse effects while writing the code. That variable could be anything. It's just an object, so it can be an integer or a float or a string, and then you can write processing on top of it. That sort of behavior is probably the worst thing about Python, in my opinion, because it allows people to get down that road that you just described, where you introduce complexity that is impossible to repair after you release the code.
Right. Yeah, it's not just Python. I mean, it happens in every language. Although I feel like it happens more in Python, but like, it happens. It happens a lot everywhere. I mean, it happens anytime you have a function that where there's not a clearly written like doc for it. Because then at some point someone's going to come along, and how in the whole world are they going to know? Like, it's just impossible. They're going to have, like you said, some good intention, and or sometimes you get into. I mean, you see it at work too. I see it in open source. You see it everywhere. Like there'll be discussions where someone will be like, "Well, what should this fix be?" And if people are arguing, should we fix the caller or the callee, or should we change whatever? And like fundamentally, they're arguing about like what the contract is. Like they each have a different conception of what the function's contract is in their head, and there's nothing written down that says like, well, no, it's actually this one. And so then it's just people like arguing about like what it should be, and you're like, well, if there's 1,000 programs that all call it, man, you really hope that they all have the same conception of what the contract is, and like that's the one you need to code, you need to respect. But if it's not written down, then I don't know how anybody knows what it is. Like,
well, here's the alternative, right? Is you have a crap ton of assert statements that say, is this type an int? Is this list under length n? What are your guys' thoughts on just starting every function with like 15 lines of validation?
Oh yeah, well that's part of the contract, right? The contract will be like, argument 3 is an int, or whatever. I mean,
yeah, but for a non-strongly typed language.
Oh yeah, well, I mean, I would do that. Yeah, I mean, if that's really the contract, then that it's an int, and if it's not an int, the caller is wrong. You know what I mean? Like as a writer of the function, you have to decide like what needs to be true for your function to do what it needs to do, and then you need to make your function do it, and then you got to write down what all those things are, and then you should check. You should have like code at the beginning that detects any error, any violation of that contract you can. Like if the third argument needs to be an int for your thing to work, then yeah, totally assert like it's an int.
Yeah, and I would say in Python, a pet peeve of mine is seeing a large library where people are doing raw asserts at the beginning of every function, which is effectively just copy pasted validation throughout their entire code base. So I like just utility functions that are created. They're private. They live in a utils directory or something. And you're like, hey, I need to verify that the list of strings that are in here are properly formatted URIs. So I have a utility that just does that. It just does a list comprehension and then throws an exception if it detects something that's not formatted correctly. But rewriting like that validation at the start of every function, I have seen people do that before in Python in particular. You're like, what are you doing? Like your function is now like 800 lines long. Nobody can read this.
Right. Yeah. Right. Copy paste code. Right. Yeah. You have something you're doing 3 times, you should put it in a function and call it. Yeah.
Yes.
Yeah. Right.
100%.
Yeah.
What about 2 times?
I don't know. 2 times. I'll allow like the first time you do it, you don't need to copy it. That's 1 time. The second time, maybe it's not a pattern. I mean, the second time, maybe you should do it too. But the third time, you should definitely do it. You know what I mean? Yeah. I mean, sometimes you add like, sometimes people go too far in their attempt to like not copy and paste code. They make it more complicated. Where you have like a function that calls a function that calls a function that calls a function that turns 3, and then you're like, what does that do? And you're like, it gets the 3, and you're like, well, I'm just write 3. It would have been way less code. And they're like, well, but the 3 would have then like, I saw somewhere else there was a 3, and it's like, and then someone's like, well, what if it's not 3? And then you're like, oh, well, we need a meta config that tells us which of the numbers we intended to use. And then, you know what I mean? Like you see like a function, it's like get 3, THREE or something. And then that function calls, get, and then inside of get, it's got like some kind of switch or if statement branches where it's like, if it says THREE, then return 3. And then you're like, I mean, I'm like incredibly exaggerating, but I assume you guys have seen stuff like, yeah, sometimes it's too complicated. It's like whatever makes it most readable. You know what I mean?
I can confirm. I've worked with a client before when I was doing the consulting thing, where they took the dry principle to such an extreme length that they didn't really understand what was wrong with what they were doing until I intentionally threw an exception with their code, like just modified something and threw at the end of this chain of nonsense that they had created. I was like, can you tell me from this stack trace what actually caused this or what went wrong? And I was like, here's your function, your main function that I just threw in. And I'm going to remove that whole call stack and I'm going to just create the logic. And it turned out to be like 2 lines of code. And it called 37 functions throughout their entire code base.
Yeah.
And I was like, let's get the core logic of what this is doing. Let's look at the stack trace. And he compared the two. I was like, look how many pages I'm like scrolling in front of him. Like, see how many pages are in this stack trace? How usable is this? Like, is it worth it to do this level of abstraction versus keeping it a little bit simpler and just using one utility that'll do this?
Yeah.
Like, I thought I couldn't. Thought I had to have like abstraction everywhere. Like, did you just like take some course online about software engineering fundamentals? Yeah, I just finished it 2 weeks ago. Like, okay, welcome back to the real world, and we don't do this.
Right. Yeah. There's a lot of kind of stuff. A lot of things like, well, this is like a best practice, and you're like, no, the best practice is you make this usable for humans. And you're like, is this good for humans? And then you're like, you always got to ground things. Sometimes I worked for 10 years and then like working for defense contractors and government stuff. There's a lot of conversations you have where you're like, we're doing this thing. And you're like, this is what we're supposed to be doing. It's contract says. And you're like, yeah, but is this a value to any human? And then they're like, I didn't think of that. And you're like, you should think of that. You should always think of that every moment of your life. Like, am I doing something that enriches other humans or not? There's a lot of that. Another one is, what's another example? I had an example in my head a second ago when you were saying that, but now I forgot what it was. What's the thing there you're looking at? Was it like a domain specific language? I feel like that's another like failure mode that's similar to this. Someone's like, our program needs to be really configurable. It needs to be, you need to be able to change it to do anything. And so rather than saying like, well, there's a programming language that is very configurable because it's the programming language that's made by programming language experts. And it's like the tooling you have. They're like, yeah, what if I made a config file that like configured my program, and then I made a domain specific language that you know what I mean? Like they write in Python and they write this giant interpreter. It's effectively a giant interpreter, and it's so complicated. And all it says is like the config file says like print 3, and you're like, why don't you just print 3 instead of like 500 lines of like, I feel like was that what you had? Was it like basically a DSL?
Not with that use case. That was just an ML project that they were writing, and they wanted to take cookie cutter templates and then just go in like insanity level with trying to introduce design patterns into a Python project. It's like the entire thing could have been written with like a functional and like descriptive style of programming with just less than 20 functions in 3 files, and it would have done the exact same thing. Instead, it was, I'm pretty sure that project was like well over 500 files and over like 1,200 functions were defined within them. A lot of them were effectively no ops, like just ridiculous assertions, like throw if input is a string and I'm expecting an int. Like, just can you just do the negative of that? Like, it should be an int, and you don't need to like write a function for that. But I've definitely seen DSLs before, some comically complex ones where somebody gets it into their head like the world really needs like a sequel to Python transpiler. Like, does it? Like, who in the did the world tell you this in your dream last night? Like, is this something that's useful for humanity? Like, why not just use SQL? Like, it's already a DSL that interfaces with database systems, and it's pretty great and universally accepted. No, but I need something that'll, write Python code for me from this interface. Just learn Python. Like,
right. Yeah. There's a lot of desires are born of like, programming is hard, so I need a thing that does the programming for me. And you're like, what's that thing you're gonna make gonna be? And they're like, it's gonna be not a programming language. And you're like, is it? Are you sure? Like, yeah. And they're like, no, it's simpler. It's just like a little config file. And you're like, is it a config file? Like, you have a conversation. I have a conversation where I'm like, okay, so it's just a text file that ends in .py, and it lists all the things your program's going to do. It's just a text file. You just edit it. Can we call that the config file? And then we'll just have a program that runs that. You know what I mean? They're like, no. I'm going to have another file that's called .cfg, and it's got instructions to tell it what to do. And you're like, okay, well, why don't we just delete that file and put the shorter thing in the .py file, like, or we just rename it. You know what I mean? Like, we'll rename the CFG file to py, and we'll just change this. We'll change the text a little bit, and then we'll tell this other thing to run it. And then, you know, and they're like, sometimes they're like, oh yeah, right, like, yeah.
That's the crazy thing that I see with people that are getting into data science that don't come from a CS background, is like I don't know what it is about somebody seeing code for the first maybe year of their getting into the field.
Yeah, it's like terrifying.
Yeah, they're like, oh my God, this is so complex. And then, you know, to somebody who's a seasoned developer, like, yeah, Python's pretty easy. It's pretty straightforward. It's really nice, high level language. You can break stuff with it, but you can do some cool stuff with it as well. And then like, I've shown people what compiled languages look like. So I used to write an awful lot of Scala back in the day, for ML use cases as well, for like distributed computing. And when you show like a data scientist who's relatively new, you show them Scala code, they're like, whoa, like, what's with all the colons and the arrows here? Like, well, it's another, you know, language. It's strongly typed, but it's compiled. They're like, whoa, yeah, it looks complicated. It looks like this is compiled. I'm like, no. This is the human interface to the compiler.
Right.
I'll show you what the computer sees. You go and like open up a jar file and show like bytecode and be like, this is the instruction set that the JVM is executing. They're like, whoa, that's crazy. I'm like, yeah, that's why we don't need to simplify Scala. It's already simple compared to what the computer is doing. And if you go one level down, like what the JVM is actually sending instruction sets to the CPU, it's like, that's ancient Greek to a human, except maybe you took a bunch of assembly.
It's been a while though. been a while. Yeah.
Yeah, speaking of assembly and things like that, I was wondering if you could chat a bit about Aurora and what tech stack you guys use. What are sort of the design principles? Do you guys enforce things like contracts? How do you guys write code?
That's a long answer. Well, I mean, we use PyTorch. I love PyTorch. We used to use TensorFlow, but I convinced everybody to switch to PyTorch because it's just better. I don't want to go on a TensorFlow rant. As tender as I am. So we use PyTorch. I mean, so I should back up. The car is written. All the code that runs on the car is written in C++, because C++ is like, it's not really reasonable to write Python and on a real time system. It's just not. It's like really slow, and I mean, like, if you write a loop in Python, it's like nominally going to be like 4,000 times slower than a C++ loop. So, you know, if you had something that was going to take a millisecond, that's plenty fast to respond to something. But if it takes 4 seconds, that's really not good, right? And that's a big difference. And then that says nothing about like trying to optimize like a bunch of high level data structures or like some larger program. It just snowballs from there, and you end up with like one of my pet peeves is running cloud code that costs $100 to run, and then but it's all Python. And then I find out like, oh, if I wrote that in C++, it could be like a page of code and it would cost a penny to run instead of $400 or how much I said. But anyway, so yeah, what do we do? High level. So like the car runs C++ code. It loads in PyTorch, like script files, like or the PyTorch, like the PyTorch JIT files, and we run those. And then we use like TensorRT too. You can like package TensorRT inside of that. So that's kind of how we do. Like there's a ton of C++ though around it, and it does all kinds of, like, it would take a long time to explain. There's like sensor data flows in, and there's like custom CUDA code we wrote. Like I wrote a library to make custom CUDA, to make writing CUDA easier. Like, I don't know if you guys have written CUDA, but like most people have this feeling that writing CUDA is like super hard, because when you look on the internet, all the examples are like this like gnarly C code that looks crazy. Yeah, it looks awful, but the CUDA's compiler, NVCC, supports C++, like modern C++, which is like way nice and clean and like so simple. And you can make this cleanest stuff. So like I got everybody doing that when they need to. So there's always times in like Python when you're doing something like you've got like an array of ladder points or something. You need to do something that isn't like in a library already, which happens at work, right? Because you're like doing something new, and you can't just like pip import like self-driving. You have to write new code. And so like, if you can like, oftentimes you can chain something together out of like 50 NumPy functions or 50 PyTorch functions or whatever that eventually does it, but it's like super complicated. The code is way more complicated than it needs to be. And when it impacts the hardware, it makes like a hardware engineer at NVIDIA cry if they found out what it was doing to like get the answer that you're trying to compute, right? Whereas like if you could just write it in CUDA, you could write one little function with a for loop with 3 if statements and it does it, and it runs like blindingly fast. So we do like a lot of that. I don't know. Do you want me to go in a particular direction? Oh, yeah, there's contracts. I love contracts. I try to get as many people to like write clear contracts as they can.
Do you actually take and wrap those interfaces with like Python so that Python developers can use your C++ module that you've created?
Oh, like the CUDA stuff?
Yeah.
Yeah, well, PyTorch has a really great, they have like, do you guys know what PyBind 11? Oh man. Okay. PyBind 11 is wonderful. PyBind 11 is this C++ library that makes it really easy to write Python extensions. So it's like type safe, and it's not C. Like the Python API itself is a C API because Python is written in C, like the main Python interpreter. And like everything in C is a pain. Like C doesn't have like automatic anything. It doesn't automatically delete variables. It doesn't automatically free stuff. It does implicit casts all over the place that would surprise most people coming from not a C background. But C++ is really clean in type. So you can write C++ that looks like Python, and like C++ is like totally automatic memory management, all that stuff, which is also surprising depending on where you're coming from. But it's true. It's been that way forever. It has the option to not be automatic, which you have to opt into, but the default is automatic. Anyway, so there's this library called PyBind 11, which is just wonderful. Like you can write a function in CUDA or C++ or whatever, and then one line basically you can just bind it. You write like this is the function name, and then like just list out the arguments. You can have a doc string in there, and bam, you compile it and it appears in Python. You can just call it, and it's just wonderful. It's like type safe, and it's so easy to do it. So anyway, it's like the thing that everybody uses if you're binding like a C++ library, or even if you're binding a C library, probably you do it at this point. But anyway, the Python, I love the PyTorch team. They did such a good job on like almost all parts of it. They have an API that lets you write PyTorch extensions that they just cribbed the PyBind 11 like interface, like the way it works. They did the same thing, but like for their types, and it's very slightly different in ways that make sense for specifically interacting with PyTorch. And so like it's so easy. It's like you write a function you want to write in CUDA or C++, and then you add like this. I should say it out loud. This is a podcast, right? No one's gonna see the video. You add like 3 lines of code, and then it just declares it, and then it appears in PyTorch, and you can just call it, and you can use it in PyTorch like modules you're going to save out. Like it's a first class object. I mean, it's literally like how most PyTorch functions internally are written, right? That's the library, that's the API they use to write all their stuff. Because I mean, PyTorch is just a Python interface to a bunch of C++ code.
Right.
So like, it's wonderful. Like it's so great. It's one of the reasons we switched to PyTorch. Whereas like writing extensions in TensorFlow is like
unpleasant,
really frustrating, like to put it politely. Like, yeah, it's not a great experience.
So you natively get with their connector and their implementation, you can get like torch data types that'll come in, like their custom like bfloat 16, like I need a tensor of this type, and that's when I'm going to be using it, as part of my contract for my own code. And you don't have to write that implementation.
Yeah. They have a real interface and like a real API. Like realistically, TensorFlow doesn't have an API, like a C++ API. It has a pile of code is not an API. You know what I mean? Like it has,
Right.
they're like, it's open source. You can like get the code. Whereas PyTorch has a really good API. Like we actually use PyTorch has a tensor class, like a C++ tensor class. It's like they use it everywhere themselves, and we use it in a bunch of places too. And it's like, it's great. It's super great. Like I mean, they have docs on their website, or PyTorch docs about how to do it. It's really, really amazing. I wish I could open source the CUDA stuff we have for writing like CUDA extensions. One of the nice parts about it is like cool. You can write in CUDA, or you can write like you can write one function, and it says like for all of the whatevers do the thing, and then you can run it on the CPU and the GPU. Like I feel like one of the things that gets people is they want to be able to run their code on CPUs and GPUs. And if you have to write two separate implementations of it, you're never sure, like, are they really the same? Like, and so whereas like, so with templates and like, there's a way to do it in C++. If I showed you, you'd be like, oh, okay. You can write like one function that does it. And it's templated on a type. This is like, am I on the GPU or the CPU? But the user doesn't really see that. And then it compiles like under the covers, your compiler infrastructure compiles it twice.
Right.
And that lets you do like 98% of all the things that a PyTorch user want to do. Like there's stuff you can do in CUDA that doesn't fit that mold, but so much of the things people want to do in PyTorch are like so simple that thing works. You can get into like more complicated CUDA stuff that's even faster, but if your first experience is like, I wrote this one function that is as simple like Davis is describing, and it made my Python code like 4,000 or 100,000 times faster, or whatever the speed up is. Maybe it's only 20 times faster. It could be you're already like really pleased, So
yeah, that actually makes me start thinking about a tutorial that I'm working on right now, which is RAG applications for using like LangChain and MLflow. And for that demo, I chose another Meta AI product, which is FAISS. So they're basically their vector DB implementation. It's like an in-memory vector store that has all of this cool stuff that's packaged into it. But they go real hard on creating very simple APIs that are incredibly intuitive to interface with. But then under the covers, they're doing, even with that project, which was released in, I think, 2017, it's still maintained, but they really spent some time looking at what do we need to build here with respect to getting performance. We need something that is cookie cutter enough, like simple for making a demo and for just testing stuff out really fast in a quick and dirty way, but then also something that can run on CUDA, and we can do similar stuff to what I've seen in the Dlib library, interfacing with BLAS operators to get maximum performance, but having that also run on GPU. And when you actually deploy that thing, like face onto a GPU and load it up with 1 billion embeddings and say, like, I'm going to see just how performant this is. Like, can it actually do what it claims? And then sitting back and running it and be like, wow, I just searched through 4.7 billion documents and said, return top K matches, top 50 matches on search. And it returns in 17 milliseconds. And it's accurate.
It's pretty good.
It just... But it speaks to like the engineering talent there, where they're not just focused on let's build something cool. They're focused on let's build something useful. And it's easy and intuitive.
Yeah, it really comes through. I mean, it's amazing. Like, yeah, like I don't know how they were able to build that kind of culture there. I mean, I get it at some level, but like, yeah, they did a really amazing job. Like that was literally, that's one of the reasons we switched to PyTorch. Like we used to use TensorFlow, I was saying, and like it comes through. Like it's so clear that they thought carefully about the APIs and like all the things you just said, and it's really great. I love it.
Yeah.
They make great tools.
I'm huge fans of meta engineering, like massive fan.
Yeah.
I also love some of the stuff that Google comes out with. Like we don't take sides on MLflow. We integrate with everybody. That's a very popular package. But there's noticeable differences when you're interfacing with these different libraries that are effectively doing the same thing. And you can see it in the number of lines of code for integration to do the same functionality across these two libraries. One of them is 10 times longer than the other in just Python interface code, because the APIs are far more complex. They're more low level, arguably more powerful if you are willing to invest the time and effort to do it. But most people don't have that kind of time or money or desire to play around with like low level APIs all the time. I'm interested on like your take on that for usability between these different frameworks, between you building something that's pretty awesome and comparing like what that focus is with the contracts, as well as how you see some of these major open source packages you use for doing this sort of thing. What makes you choose one over the other?
Well, I mean, it's like I said, like things have got to have simple building blocks that then like let you do more complicated things. But like good software is like an onion. It's got a lot of layers. So like, yeah, sometimes you see tools where they're like, well, it's really low level and it's hard to use. Well, they should think about what their use cases are. I mean, maybe their whole game is like, we're only for the low level blast library and we're not interested in doing something else. And that's someone else's job. And that's fine. But like, I feel like a lot of tools you see, there's no like design internally. It's like just a big brick of spaghetti inside. And it just has like the one interface it has. And like, then people will say like, well, it's hard to modify or extend or whatever. Because as soon as the API they give you doesn't meet your needs, you would want to say like, well, let me just send to like whatever their internal lower layer is and like interact with that instead. So I can then have more power. But that lower level like doesn't exist. I mean, it exists in some base level of like, well, there is the software and you can just get it and it's just text files in a folder and you can do whatever. But, you know, if it's actually the lower level is actually a bunch of other functions that are well thought out, that are documented with clear contracts, then you can be like, oh, great. It's just some other like part of the library I could be using. I don't normally use it, but when I need to, I go there and it's just as clean and well thought out as the other one. And then under that one, you know, it's like underneath those functions, you might be like, well, sometimes I have to go even further down. Mm-hmm. And like, is that again another level of clearly thought out API that has a bunch of simple building blocks that are all clearly documented and put together? If it is, yay, great. You're like fully empowered to do anything. You have the same level of power that anybody working on the project might have, who might have a really deep understanding of it. And which is like mostly how PyTorch is, for instance. I was talking about PyTorch, other things like this too. I also love SQLite. I think SQLite's really well written. It's wonderful. It's like really wonderful. So, I mean, that's kind of what I look for, right? Like, is it just a ball of spaghetti underneath the first layer, or is it like an onion with a bunch of nice layers in it? And then if it is, then you can do anything. There isn't this like, oh, it's too low level or too high level, because you just use whatever level you need to use.
Yeah, that plugin architecture that you're alluding to with the onion layer. Like, I've seen it where certain libraries will, like, the onion exists, but then you can clearly tell that the people writing the code don't want you to access like the last two layers. They'll like warnings and notes sometimes in the code. There won't be any like documentation on those internal methods, or in Python they'll do stuff like underscore before a class name, and you're like, okay, I get it. You don't want anybody touching this because you're probably changing it all the time, and that interface is for your internal, developers only. And I can respect stuff like that when people do that. but it says a lot about the maintainers and designers of APIs when they say, hey, we're going to create this abstraction layer that is exposed. It's like a public API for this low-level operation. We're going to allow people to use it. We'll document it, say like how this thing works, and then give an example of like, hey, you can implement this and define a plugin and then call this one line, and now our library will understand your code and will process it through this plugin architecture. Provided that the maintainer eats their own dog food, like they use that abstraction everywhere in the library itself. So it's sort of like a self-documenting feature. Like, hey, you want to build your own interface to this that just works whenever you install this? Here's an example of 17 instances that we're doing the exact same thing.
Right. Yeah. I think all software should be written that way. I mean, because it's crazy. I mean, because it's crazy to do otherwise. Like if you're running a big software project, you yourself are your own user, because you're like, well, there's a lot of code I write functions, and then I call those functions because that's how software development is. And if those functions are themselves like scary, undocumented monsters, you're like, only I can call those. No one else can call those. You're like, why not? You're like, well, because no one else can understand how to call them. You're like, well, then how do you understand how to call them? Like that's crazy. Like you're gonna remember all that in your head and like somehow not screw it up. Like, no, that's not what happens. Like it just becomes this like huge weird mess, and it's becomes super hard to change. And you have to worry about like spooky action at a distance. You're like, I edited that function, it seemed fine. And then like other things exploded. And then you're like, oh yeah, I remember that 6 months ago or a year ago, we did this other thing that depends. Oh, okay. Right. And they're like, that's whack. Like, or you should have like unit tests on the functions, right? Like, because how do you know that it work? And you're like, well, how do you have a contract on that function? How do you have a unit test on it? Like, what is the test? If you can't say what the contract is, then like, how do you know whether it's working or doing what it needs to do? And like, you know what I mean? Like, yeah, I submit that like a good library is made out of smaller other good libraries that you wrote. And those other libraries made out of other tools. It's like anything. Like I tell my kids, like, if this conversation with my kid, like the tech tree of human tech tree, or like, you start with your hands, and then like at some point people invented, like you make tools and you use those tools to make better tools, and then you use those better tools to make even better tools, and then eventually you're like on a jet plane flying through the sky, and like, and it's not like, yeah, you have to like make the tools to make. Or another thing I tell people sometimes, that hopefully resonates with most of them, is like, if you have a problem in software engineering, you're like, well, you just take a stop. Like you're working on something that's like too hard to figure out. You can't make it work. Just stop and be like, what tools, if I had them, would make this like really easy for me to solve this? And then you're like, go make those tools. Like, you know what I mean? And then in making those tools, like you might find that those are still too hard. And like, well, now what tools, if I had them, would make this really easy? And then you go make those tools, and like make those tools nice. And then you have this like nice collection of tools that like make sense on themselves. And yeah, I think that's how all software should be. Well, unless you're like doing some experiment and throw the code away. Throwaway code's different.
Yeah, prototypes and stuff. Yeah.
Yeah. If you're just
then
like
get dirty and nasty, just make it work.
Yeah. Right. But as long as you're willing to throw it away.
Yeah. The nasty thing that you end up seeing sometimes with some libraries is this is clearly a hackathon project, or this was something that somebody was trying to prove that they could do, or they were trying to solve for this one use case that they have, and they don't want to like release unit tests as part of their open source code, or they never wrote unit tests. And then all of a sudden you see, hang on, this package has 400 stars. It was released 2 weeks ago, and there's no test coverage. In fact, the CI link that should be there as part of a badge for this is broken. So it's pointing to the void of nothingness. And you start wondering, like, how many people are downloading this? And you check some download stats from like Peppy Tech or PyPy, and like, hang on a second, 150,000 people downloaded this in the last 2 weeks. Is this about to become a problem?
Yeah.
And then you find out, like, oh, they had to release 18 patches over the last week, and all of them contain breaking changes. And you just sit there and wonder, like, how are they testing this? And they're doing, they're doing the Bill O'Reilly from Inside Edition. They're testing live, and it's
testing the users.
Yeah, it's
Stu gets upset. Yeah.
Everything is an integration test, and that integration test is run when somebody downloads the package and then tries to use it, and then they find out that everything's broken. It's scary to me when I see stuff like that. Just how frustrating it is for an open source user, and how much that sort of degrades the entire open source ecosystem when there's just crappy code that's out there, crappy libraries.
Yeah. Yeah, I don't know what to do about that. I don't know. You ever read the book Anthem by Neil Stevenson?
Mm-mm.
Oh, okay, dang it. I was gonna make a reference. In the book, like, it takes place, it's such a long book. It takes place way in the distant future, and like one of their problems is like the internet of the future is like so filled with crap. You have to have like this really deep like level of ability to filter out all the crap to be able to like not just be like inundated with garbage constantly. And like anyway, it's a great book. It's about other stuff though.
I mean, there's parts of the internet that kind of feel like that today.
Yeah. Well, it's even worse. It's like, imagine in like 50,000 years in the future, I forgot how far in the future, where it's like you have to have like AI meta filters, and like, or you just like, as soon as you open it up, you're just like, where am I? What is happening? Like, yeah.
So
I don't know.
Spam.
What?
Yeah. So I have one more topic, just shifting gears a little bit back to a prior topic. So we've been talking for like the past 30 minutes about ideals in software. In your experience, Davis, at Aurora, are these ideals correctly implemented? Or what are sort of the strengths and weaknesses of your stack, and what are you working on day to day to make it better, other than this CUDA implementation?
Oh, no, it's pretty good. I'm really satisfied with it. It's the
Nice.
cleanest, best software I've ever worked with. So,
Wow.
yeah, no, I'm yeah. I mean, but like,
Yeah. So what's
nothing's
on the
ever-
cutting edge for you guys then? What are you working on in the next 2 to 5 years, or even just in the immediate future?
make the car good enough to drive without a person in it. That's the only goal. I mean, that is the only goal. It's almost there. It's like, it's pretty good. I mean, like, probably the thing I complain about the most is data quality. This is a thing on every ML project. We're talking about ML stuff, right? Like, the thing that I feel like most people take for granted, or especially if they come right out of grad school, is like, it feels to a new graduate as if the data is a given and you can't change it. Like, if you were in grad school, you can't just edit the labels, because that's cheating. Like on the benchmark, right? There's some benchmark test that you're going to run your algorithm on and compare to the papers. And if you, as part of what you did, you went and edited the labels and cleaned them up, and then it's like, man, my method's like way better than everybody else's. You're like, well, why? Well, I fixed the labels and data and I made it really appropriate. That's not like a publishable result. That's not like in the spirit of what you're trying to do. You can't say like, and therefore my math is better. So that's like not a thing on people's consciousness. Or like, I get a lot of questions in Dlib. I swear this is going to come back to Aurora. I get a lot of questions from Dlib users that are like, I'm trying to make this image classifier or something or whatever it is. And then, they post their data, and it's like clear that it can never work. So like an example that people do a lot, maybe the most common kind of mistake new people do, is they're trying to make like an object detector. And so they'll have a bunch of examples of like, maybe they're trying to make face detectors or something. So they'll have a bunch of examples of faces that are like really tightly cropped images, and they'll draw the box that is on the image, like the whole image. Right. And they're training the model to like be like, say that's a face. And then they take that model, and then they run it on a whole image, and they're looking for like where in the image are faces. Like, that's not going to work. But that requires like an understanding of like how the algorithms, like how a CNN works, and like appreciating that it's going to like learn. There's going to be like these border effects that are going to screw it up. It's going to learn like faces are surrounded by border effects constantly from like the convolutions, or depends on that, just or like a hog filter, even like a practically any version of any like scanning object detector ever would like be foiled by that. And like people who are experts know how to do that. And like that's like a basic thing. Like, is your data appropriate, or like are your labels okay? Like you could give it a bunch of images of, if your negative examples have a bunch of faces in it, it's not going to work, right? Because you're asking it to say, like, let's say these are faces, but then say these other faces aren't faces, and then it's just going to get confused. It's not going to work. So like in self-driving, it's way more nuanced than face, not face, right? It's like you need to find all of the things. All right, it takes a while to even explain it. So you need to find all of the things that you should find, but there's going to be stuff that's impossible, right? There's going to be things you're not going to be able to see. Like there'll be like fire hydrants behind buses you can't see, and you're like, okay, well, does it matter that I can't see it? Then does it matter now that I don't know where that fire hydrant is? Like, does it matter? Like, if the fire hydrant was in the middle of the, like, if someone like took a fire hydrant, unbolted it from the wherever it was, and put it in the middle of the road, you better not drive into it. Or like, a naive metric might be, if there's a person, you should always see it and tell us where it is, because you shouldn't drive into people, which sounds totally legit on the face of it. But if you then like have humans go annotate data with where all the people are, they're going to be a whole bunch of people who like are impossible to track and don't matter. And then you'll be like, well, who? And you'll be like, well, we noticed there were people sitting in McDonald's eating sandwiches, and like you could see them through the window, or maybe you like saw them walk in and you knew they were there because you can reason it causally, like that little patch of brown above the window frame is the person, because you saw them walk in and you saw the brown go over there and sit down. And so that's like Davis's hair. And, and if you're asking your ML system to like say which McDonald's patrons are sitting in which seats behind like the wall, then it's going to overfit and be weird.
Right.
And there's like the unending there's unending amounts of this kind of thing. Or like you might say like, we should track children. We should track children. But then you say fire hydrants again, right? Like, well, how does that relate to whether we should track fire hydrants or not? Well, in LiDAR, fire hydrants and children look really similar. So if you accidentally don't label fire hydrants, you're basically saying like, well, things that look like children in your sensor data, like maybe don't tell anybody about those. And you're like, and that will then harm your ability to track children because you haven't labeled fire hydrants. And so like the challenges are getting like the data to really, really represent like what you need, like the labels and the data you need and all of that. And I think that's like the main thing like everybody in this industry struggles with, because your models are only going to be as good as your data. I mean, they can be a little bit better, but that's kind of the main thing. I mean, but then when you get into the details, there's like tons of code and there's all these algorithms and they have to be correct and they have not have bugs and they have to be validated and all that stuff. But
yeah, it's an interesting reframe from data quality to data quality for the problem.
Yeah. Yeah.
So like, yes, you would like to have a perfectly labeled data set, but sometimes, as you said, labeling everyone in McDonald's that's eating a sandwich, that's not the data for the problem. That's great data, but it won't lead to the correct algorithm output. So that's a really cool differentiation.
Yeah, there was I listened to some of your podcasts. I forget, one of the ones you had someone talk about this. Like, you need to see like, what does our business actually need? And then you need to construct your problem such that it's like specifically about that, rather than like just have high F1 on this data set that I didn't really pay careful attention to. I think some of them, he had more than one guest on about that, and which is great. It's like, everyone needs to understand that better. It's like, if there's one problem I could point out in the ML industry, it's like a lack of understanding of, or a lack of a willingness to look at your own data and be like, does this make sense? Like, is this really what we need? Yeah, that's it's a never ending grind. But back to the people in McDonald's, it's like, we do need labels on those people. Cause like, because otherwise what happens is like, well, the model sometimes it'll be able to see them and it'll be like, I'm really sure it's a person. Look at the whatever, And then if you don't have labels on that, now you have training signal says like, okay, well that time, don't tell me about that person. And the model is going like, what are you talking about? Like, I could totally tell it was a person that time. It was really clear. because of whatever in the sensor data. It was super clear. So you still need it, but you then need to you need to be able to say like which matters more. If you're going to make trades, like your loss function fundamentally is about like making trades, right? It says like, okay, which matters more, detecting the person standing in the road in front of you or all the people sitting at McDonald's? You're like, well, detecting the person in the road, or it's like, it's about having false positives versus false negatives, right? Like the trade will be like, I can either detect the person in the road, but if I do that, then I'm going to necessarily must also detect all the people sitting in McDonald's some fraction of the time because they're also people. They look similar. And is that bad? Or maybe there's bushes that look like people. There's a lot of bushes that look like people sometimes. And you're like, is it bad to say don't drive into bushes? Would you want to make a trade that's like, I can either not drive into a person in front of me and sometimes not drive into bushes, or drive into the person in front of me and sometimes drive into bushes? And you're like, well, when you phrase it that way, it's like pretty clear how to construct the loss. Right? You should say like, well, I don't really care when I call bushes people because I shouldn't drive into them either. But then anyway, it goes. I could go on and on for hours about this. I don't know if this is boring or not.
No, it's interesting stuff. One other thing to add that I'm curious about your perspective on is interfacing with a very well-trained computer vision implementation, whether it be traditional old school stuff where it's just pattern recognition in images, or the type of cutting edge stuff that you do right now. When you hook those up to a system that can take action on the output of the model, and you're not super careful with what it is that you're interfacing with, and I think this probably definitely applies to stuff that is a solved problem for you and the teams that you work with people trying to intentionally defeat the image recognition and object detection capabilities within self-driving cars. I'm sure you guys test that yourself as well. But a number of years ago, I saw this report that was somewhat related that I thought was really funny. Some guy in California thought that it would be hilarious because he knew that the speed cameras associated with like the city that he lived in, or some city that he was going through, they had no controls over what it was doing to process a license plate. So it would take the raw text that it detects, whatever it may be, with no length restriction, and just run a SQL query with that. So the guy did the first SQL injection attack with, computer vision system, but did it to the state of California in this one municipality. And now his assigned license plate has been stricken from CHP's database. So now every time that there's and what it basically did was like, hey, for my license plate, delete all rows. So he wiped out like every traffic ticket that these automated systems had ever given him. He owed like, I don't know, a couple $100 or something. He didn't feel like going to court. And it was amazing that like the picture of his license plate, it was his license plate, but then basically a drop rows statement in SQL PML. And the side effect of that for this guy was now every time that a license plate detection algorithm in that county fails to figure out what the license plate is, it returns a null, which is now mapped to his address and his driver's license number. So I guess the guy has something like $50,000 in traffic fines that have arrived to him. What do you think about when you're doing the interface to these systems? How critical is it to think about how people will mess with your system?
I don't know about the mess with the system part, but like the interface between you're saying like the interface between like the neural network and the rest of the C++ code, right?
Yes. And how that would potentially interface with stuff like the steering wheel and the brake pedal.
Yeah. So it's not like, right. Sometimes you read about people trying to do these like end-to-end systems where it's like one neural network. It's like some giant black box. I mean, there's never really, I don't like the phrase black box. Like everything's a black box until you understand it. And then all of a sudden it's not. And so it's like, it's a statement about like your state of mind rather than like the system. But like, let's go with it, right? So like there's this neural network and it's hard to know what it's going to do. And you might be unsure about something about it, like given some input, what's it really going to do. Although you should you test like crazy. We have like petabytes and petabytes of tests we run through all these things. But like still, right? You still want to be able to make like really strong claims about what's going to happen. And so we don't do any, and I don't know that any of the real companies doing self-driving have like an end-to-end learned system for the reasons you're talking about. So like what happens is like there's a module that just shoots out boxes, right? Like XYZ center and length, width, height, and angle, basically. And so like that's this constrained thing. It's a type, like in C++. It's got those numbers in it, and there's no possibility of it mutating into like a SQL drop statement or any kind of weirdness other than just a box. It's just a box. And then there's a lot of like there's a Kalman filter. There's like extended Kalman filtering, and like there's a lot of classical robotics and geometry and like real stuff that you like know the answer to. It goes into that, and like that does reasoning about like physics and things in motion and like all of that kind of stuff. So like we're not learning, like you don't want to learn, like machine learning should be a method of desperate last resort, where like if you just know the answer from like physics or geometry or whatever, you should just code that up carefully and then like unit test it and be like extremely confident that it's correct, and then use that instead. So like in our system, basically what happens is there's LiDAR, camera, and radar, and so there's some neural networks that shoot boxes out. I really need a better prop than my hand waving around the air, but it shoots boxes out. This is like, I think there's a person here and a car there, and then those get turned into tracks. A track is just like, I think there's a person there and I'm following it, and then there's a tracker that runs on top of that follows it around. And then it would take a long time to explain how the tracker works. Probably not supposed to, but there's like a deep neural network inside of it that's like saying where things go. But then there's like Kalman filters and classic geometry and like things where we can be like, I'm confident that this is what's going to happen. And it's like the failure modes that could possibly happen are like really, really clear and known, right? The failure modes are like, we just don't follow it. Like we see a failure mode would be like, a car is driving over there and we think it's there, but then we make a mistake and we think it's not there, which is like a really bounded thing, rather than saying like someone, like there's no possibility of someone driving like a car with a weird zebra stripe on it that makes us turn the steering wheel. Like that's impossible. Because there's no, I mean, like the output, like the system runs, the tracker runs, and the output of that is again just boxes with their trajectories. That goes into a motion plane system, and the motion plane system doesn't have raw sensor data coming into it. It's just reasoning about the motion of these moving boxes and the lane geometry and like the lane lines and like stuff like that. So there's no opportunity for any kind of pollution from weird like barcodes or, no one can make some weird like Rorschach pattern they put on the side of their car that causes us to like hit the brakes or, you know what I mean? Like,
right.
The only way it would happen is if somehow we came to believe there was like a stopped car in the road in front of us, for instance, then we would stop to avoid hitting it. We would have to like look at the sensor data and be like, I believe there's matter there I shouldn't hit. Which would again be represented in terms of like, it would come into one of these models and it would shoot out a box that says like, yeah, there's a jackknife truck on the side of the road. But even then, those things are like, they're local. It's not like a giant GPT transformer that takes all the sensor data in and shoots out boxes.
Right. Like
for us to make a claim that there was a stopped car, some position in the world like over here, there would have to be sensor data over there that like itself sustained that claim. It's not possible for like you to show a picture. Like you couldn't be standing on the side of the road holding up some image that caused us to think there was a car 300 meters away somewhere else. Like given the structure of how like the drone are set up, there's no like data flow path for that to even happen. So
yeah, it was a perfect explanation of like the safe and conservative way to employ ML in the real world. I can't even tell you how many times I've seen people attempt to build that monolith
Yeah.
Of like, hey, we have all this data that we're going to use to control our interface, our automated interface with our customers. And maybe it's definitely not in the scope of, you know, self-driving cars and the seriousness of that. But somebody will say, we have all this unstructured data. We can just throw it into PyTorch and then, you know, get it to solve this problem. Like, that's when it goes into that you don't really know what's going on here because you haven't even analyzed your data. You don't even know what's in there. And what problem are you trying to solve? Like, how did
Right.
do all of these bits of data have anything to do with that problem? And they go and just build it, and then they run it, and then somebody finds out. I've seen it with people attempting to use like complex deep learning solutions for something that's inherently simple, like fraud detection. Robust systems that are like that are multi-layered. They have fallbacks and safety catches and, you know, detection for, you know, hey, this is something I've never seen before, but this is abnormal behavior, so I need to alert a human. Like, hey, please intervene here. We're going to place a hold on this transaction while somebody reviews it. And then also the data science team gets an alert saying, hey, you might want to retrain your model because we found this new attack vector, and, you know, do some feature engineering, figure out how to detect this. But compare robust systems like that to the monolith, and people are just like, it should learn everything magically. We retrain it every day. And it's like, what are you doing?
Yeah.
When somebody finds out an exploit and figures out how to defeat your system, that's the stuff that never makes it into the news, but I've definitely seen it at customers before, where I'm like, why are, like, I thought 6 months ago we were talking about a Keras TensorFlow model that you're handcrafting to solve this problem, and now you want me to talk to you about what I said 6 months ago about you should use like a series of logistic regression models here because those are easy to explain and control and retrain. Why do you want to start listening to me now? Like, well, somebody figured out
better.
a way that that we couldn't detect, and we lost, you know, $7.5 million in a week. Like, yeah, that's why, is you can't even tell what's going on in that system.
Right. Yeah. Anything that's like super high dimensional, or when there's like the conjunction of like this and that, but not that. And then you get into this, like, if you know, you have n Boolean statements, right? And the number of like possible things you need to have data to cover that is like 2 to the n. And like, if that's really what your problem is, then I don't know how you ever, that's hard to know your system is going to work right, you know, because you're not going to have data to cover all that. So
exactly.
Yeah, you gotta decompose it into pieces. I mean, I don't know. Someone's going to listen to this like in 30 years, maybe, and they're 100 years or something. They're going to be like, no, GPT-50 like is alive and it like does it all, you know. But like, we don't have that right now. Yeah.
Yes.
Yeah.
We do have the tools and the high enough level APIs to allow unwise people to build super dangerous stuff, though.
Yeah. Right. Yeah. Someday that'll work. But yeah, you know, to make that really work, no one knows how to do that work. But it's gonna depend on like some huge like self-supervised model that like has learned all of the, or like how does my kids work, right? You can give a human like some simple instructions, and it's like they don't learn from those instructions how to do the task. They like come do it because they've got like 20 years of this HD video and like all this data they've accumulated and somehow packed into their head. And then you give them this little extra instruction and they're able to do it, right?
Right.
So like that kind of thing, yeah, then it could possibly work because you have to like know that like human has your like appropriate value structure and like is gonna not just gonna be like, thank you for the information, lets me know how to rob you. And you're gonna be like, oh, that's not what I wanted. I wanted you to like make me happy. And you're like, you know, yeah, that's what people want though, right? They want because people see this deep learning stuff, they're like, oh, it's the thing that lets me not think hard about what I need to do and like not clarify my ideas. And I just tell about my life and it'll like satisfy me and make me feel good and make good things happen. And you're like, it's not that good yet.
No,
it's going to be a while.
A long while.
Yeah, it's going to be a long while, right? I'm not not worried that's going to be like well, I don't know. Hopefully we're surprised, and 5 years from now we're like, wow, who knew? Like, what? I wouldn't bet any business deals on it.
No, most certainly not.
Yeah.
They're clever, but they're very limited in what they do now.
Right. Yeah.
Cool. So we're sort of coming up on time, and this seems like a potentially logical breaking point. So I will quickly wrap and then kick it over to Davis if you guys want to reach out.
Sure.
So we talked a lot about sort of self-driving cars and just software design for that functionality, but software design in general. A lot of really cool points that stuck out to me. First, when thinking about an error, just because the callee or the function that is being called throws an error doesn't mean that that function is the problem. Sometimes you need to take a step back and think about if the contract was violated, and thereby it's the fault of the caller of the function. But it's really important that you explicitly state what the contract is for that callee. And then if you're also looking to enforce a function contract, make sure you leverage utils so it's scalable and dry. If you do something more than twice, maybe 3 times, there's that debatable cutoff. Try to add a util to make sure that you can reuse code. For machine learning, specifically, make sure that your data is correct for the input or to solve the problem that you're looking to address. And it shouldn't just be accurate. It should facilitate training a model that solves the problem. And then some other random software notes. Real-time systems aren't typically written in Python. PyBind 11 is a great lightweight header-only library that exposes C++ types in Python and sort of vice versa. And then good software is like an onion. It has layers. So Davis, if people want to learn more about you or your work, or specifically Dlib, where should they go?
If you want to learn about Dlib, you can go to dlib.net.
Cool.
Otherwise, I don't have a very strong social media profile, so you can go there and find out about some of it.
Sounds good. All right. Well, it's been a pleasure. Until next time, it's been Michael Burke and my co-host,
Ben Wilson.
And have a good day, everyone.
We'll see you next time.